Welcome everyone to part 2 of Keras Syntax Basics. In part 2, we're going to focus on creating the model, running our model, and then actually generating predictions from the model. In part 3 after this, we'll focus on how to actually evaluate the model's performance, as well as how to predict on brand new datasets and save and load our models. Let's head back to the notebook to continue where we left off last time. Alright, here I am at the notebook where we left off last time. So we've read in our data, done just a little bit of analysis on it, basically visualized that pair plot, and we've scaled our feature data. So now the next step is to actually create the model with the Keras syntax. And for this, we need to do two imports. We'll say from TensorFlow.Keras, and this is the way the Keras API is packaged inside of TensorFlow. We just say from TensorFlow.Keras, and then we can do any imports we want as if we had already installed the Keras library separately. And the first one we're going to import is the sequential model. And then the next thing we're going to do is say from TensorFlow.Keras.layers, we'll import dense. And this is all we need to build a very simple model with Keras. Essentially what we do is we set up a base sequential model and then keep adding layers to it. In this case, we'll just add a simple dense layer. I would also highly recommend that if you call help on either of these, such as help sequential, there's really nice documentation and various examples inside the documentation. So it actually shows you a lot of what we're going to do, which is how to construct the model and then how to add layers to it, etc. So there's lots of really cool examples here, not just for sequential, but if you also check out dense, it'll give you a lot of information on the various parameters it takes. And if you scroll down, you'll eventually also see some examples. But let's go ahead and work through how we can actually do this. Now there's two ways of creating a Keras-based model. One way is to call sequential and then pass in a list of the actual layers you want. So I'm going to pass in a dense layer, and if we take a look at dense, all this means, if we expand on this, is that it's a regular densely connected neural network layer. And all that means is if something is densely connected, it's going to be a normal feed-forward network where every neuron is connected to every other neuron in the next layer. Later on, we'll learn about more sophisticated layers, but the dense layer is what we're working with right now for our basic artificial neural networks. You'll also notice that it has quite a few parameter calls inside of it. The two parameter calls that we need to be aware of for right now is units and activation. Units is just another word for neurons, essentially how many neurons are actually going to be in this layer. And then activation takes in a string call for what activation function these neurons should be using. Should they be using a sigmoid activation, a rectified linear unit, etc. So for right now, what we're going to do is show you how we could build out a network. Let's imagine I wanted my first layer to be 4 neurons densely connected, meaning every neuron is connected to every other neuron. And then we can say my activation, and I could say something like RELU, which stands for rectified linear unit. And if you're confused on these activation functions, make sure you go back and check out the theory portions of this section of the course. But hopefully you can see the connection here between what we discussed in theory versus what we're actually implementing here of code. And if I wanted to add in another layer, I would simply keep passing these into my list. So maybe I want the next layer to have 2 neurons and another activation function with rectified linear unit. I could also pass in strings like sigmoid, etc. And you can check out the online documentation for the various string calls for different activation functions. And let's imagine I wanted one final output layer with 1 unit. I would just say dense1. Again, I could play around with the activation function there, but this is just one way we could build out the model. So that is, upon your call for sequential, you actually pass in a list of those layers. The other way we can do this, and this is going to be our preferred method throughout the course, and you'll see why in a second, is to create an empty sequential model, and then off that model variable, you add the layers in separately one at a time. So you would say activation, rectified linear unit, and then I can just copy and paste this command as such, and then kind of play around with the values here. Maybe I want this, and since this is my last layer, I don't actually want an activation, etc. So this cell and this cell are actually going to produce the exact same model. So what's the difference between them? as far as convenience, well, what's really convenient about doing this in separate lines like this instead of one giant list call is if I ever want to quickly edit or turn off a layer, I can simply just comment it out as so, and then rerun this cell, and now I'll go straight from my 4 neurons to this last 1 neuron output layer. That's a little harder to do here when we're dealing with a list. We would have to kind of delete this or maybe have it on separate lines and be careful of the way we comment things. So that's why we're going to focus on using this methodology for building out our models. We'll create an empty sequential model and then we'll add in the layers one by one. So let's go ahead and do that for our particular data set. In this case, what we're going to do is we'll have 3 layers with 4 neurons each using a rectified linear unit. And then our very last layer will be just one final output node. So the final output layer is actually pretty important, and that's going to be determined by your actual data and your actual situation of what you're trying to predict. Recall that with this particular data set, we are predicting a single numerical price value. So what I want is my very last layer to be a single neuron that produces some sort of price. So it's going to predict maybe $450 or $600, etc. That's why I'm choosing that final layer to just have dense 1, where it's just going to try to predict the price. So that final output is then going to be measured against the true price, and we'll do that with some sort of loss function. And that's where this final line comes into play, which is compiling your model. And compiling your model, if we take a look at Shift Tab here, it again has lots of different parameter calls, and we're going to be exploring these later on in the course. But the main ones we want to look at right now are the optimizer and the loss function. The optimizer is essentially just kind of asking you, how do you actually want to perform this gradient descent? Do you want to use RMS prop, or as we discussed, there's other methods of optimization, such as the atom optimizer. So I could also say optimizer is equal to, and then in the string pass in atom, which is the string code for the atom optimizer. And you can reference the documentation to see what optimizers are available for you. And then what's also really important here is this loss parameter. And the loss parameter, that string code is going to change dependent on what you're actually trying to accomplish here. And if you take a look at our Keras Syntax Basics notebook, if you scroll down, we actually have a little section here on choosing an optimizer and loss. So if you're performing a multi-class classification problem, you can really choose a variety of optimizers, but the loss string parameter that you should be calling is categorical cross entropy. If you're performing a binary classification problem, you can again choose various optimizers, but the loss here will be binary cross entropy. And in our case, we are performing a regression problem because our label is a continuous value. So in our case, we will use mean squared error as our loss functionality. So mean squared error makes sense because we'll essentially be taking the mean squared error of our predictions against the true values and be trying to minimize that through our optimizer call. So let's come back to our notebook here and then follow along with that. We'll say our optimizer is equal to RMS prop, and more importantly, our loss, since we're performing a regression-based task, is MSE, which is our mean squared error. And once we run that, we have a full model ready to go. And I'll go ahead and delete this cell so that we just see that model being created. So we have our model sequential. We add in whatever layers we want with as many neurons and activation functions that we want. We take care to make sure our last output layer matches the actual task we're trying to solve, as well as when we're compiling it, making sure our loss function or loss parameter call matches what we're actually trying to solve. Once that is done, we're ready to train the model or fit the model to the training data. And we can do this by saying model.fit. And then again, if you do Shift Tab here, you'll notice a wide variety of parameters, some of which we're going to go over in a later lecture. But the main ones I want to concern you with right now are X, Y, and then epochs. So X is simply what are the features that we're training on. In this case, it's X train. And then Y are what are the actual training labels that correspond to those training feature points, which in our case is Y train. And then epochs, what that stands for is one epoch means you've gone through the entire data set one time. And again, as a quick note, if you take a look at our provided notebook, we actually provide essentially a rundown of what this batch and what epochs mean. So this epoch is essentially an arbitrary cutoff that's defined as one pass over the entire data set. So if I've gone through the entirety of xtrain one time, that is one epoch. So I'll go ahead and say that my model is going to go through the training set 250 times, so 250 epochs. Later on, we'll discuss how to actually choose that number correctly and how we can actually use callbacks of Keras to add in early stopping so that we can just choose some arbitrarily large epochs number, and then our model itself will be smart enough to stop at a certain particular time that is optimized based off some validation loss. So keep in mind, this is kind of the simplest way we could fit, but later on, we'll become more sophisticated with our capabilities and actually fitting our model. So we'll be dealing with things like batch sizes, callbacks, validation data, etc. For right now, we'll keep it very simple, and we'll simply fit on xtrain corresponding to ytrain for 250 epochs. Last thing I want to note here is that there is a verbose call. So verbose equals 1. That essentially indicates the printed output during training. So if I run this cell, you'll notice that as it continues training over these epochs, it prints out these little reports for me. The higher the number on verbose parameter call, that means the more information is displayed. And if you set verbose equal to 0, it means it won't actually output anything. I would recommend, however, that you set verbose equal to some number that is not 0, so you can get an idea of where you are in your actual training stage. Otherwise, you just see a cell running, and you won't know if it's on the 10th epoch or the 200th epoch. Now, this is a very simple and small data set. You'll notice that we essentially finished our training. And you should also notice that our mean squared error is very large in the beginning because it essentially starts off with just a random weights and biases. But as it begins to adjust these weights and biases, so we'll scroll down to later epochs, you'll notice the loss is slowly decreasing. And it should decrease very quickly at first and then kind of slowly as it goes further and further until towards the end, it should begin adjusting to some sort of mean squared value. So we can go ahead and see this by plotting it out. So I'm going to come down here to this new cell and show you how we can actually take a look at this training history by saying model.history.history, and that returns back this dictionary of the corresponding historical losses, which means I can pass this into a data frame and say model.history.history, run that, and I get this nice data frame. So I'll set that as my loss data frame. And then I can actually plot this out by simply saying loss underscore df, plot, run that, and I see something that looks like this. So this is very typical of neural network training. You start with a very high loss during your first couple of epoch runs, and then as the weights and biases start to get adjusted, you hopefully see kind of a steady but steep decline in your loss or your error, and eventually it will level off where you're not really doing any sort of improvement in your performance as you train more and more. And later on, we'll be able to compare this to our validation loss to actually check for things like overfitting. Okay, so we just went over how to create a model as well as how to fit a model. Coming up next, we're actually going to dive deeper into the evaluation of this model against the test set, as well as how to evaluate against a brand new data point. So thanks, and I'll see you at part 3.